Consider the following statement. To show that a number is not prime, you only need to check if the number is divisible by the prime numbers less than or equal to its square root. So is 97 a prime number? Well, 100 is a square number close to that, and the square root of 100 is 10. So we only need to check 2, 3, 5, and 7. So 97 is not divisible by 2. That's clear because it's an odd number. 9 add 7 is equal to 16. That's not divisible by 3. So therefore it's not divisible by 3. We can see it's not divisible by 5 because it doesn't end in a 5 or a 0. And so we just need to check 7. Now we have a calculator available, so 97 divided by 7 is going to be 13.85 and so on. So it's not divisible by 7, and therefore it is a prime number. How many prime numbers do we need to check to see if 193 is prime? Well, 196 is a square number very close to 193, and if we square root that we get 14, so we need to check the primes up to 14, 2, 3, 5, 7, 11 and 13, so we need to check 6. Use a proof by contradiction to show the above statement is true. In other words, to show that we only have to check for primes that are less than or equal to the square root. So consider some number n which is a positive integer. Suppose n has a prime factor p which is greater than root n. Then we can say that n is equal to pa, where a also belongs to n. Now a would be equal to n divided by p, which is less than n divided by root n, since we know that p is more than root n. So what we're doing here is actually making the denominator smaller. Therefore we must have a bigger number just here. And that means that it's less than root n, since n divided by root n is root n. Now a is either prime and less than root n, or composite and less than root n, which means that a has a prime factor less than n, and since a is a factor of n, that means that n also would have that prime factor.